Now, I just want to quickly talk a tiny bit about the assignment. So if I just go into it, and it's really in relation to what I've been looking at over the last two, three lectures now, which really means it concerns, let's see, it concerns this part here, full stack web app. Now, um, in order to satisfy this part of the spectrum, you are going to have to just put together a very basic React app as your front end, and then you need to hook that up to your back end via CloudFront and all of that stuff that we talked about. Which means that you are going to have to have a React app, as I said. Now, you know, it, the Web API has three endpoints, as we know. It has two get endpoints, these two here, and it has a post endpoint, uh, two gets and a post, yeah. So that means your React app is going to have to support those three endpoints. Now, like I say, I don't really care how you design the front end, but for example, you could simply put together something like this, and this is only a suggestion now. You can do it whatever way you want to. So this might be just a single page, and sorry, no, this is just single view if you like. And so this part of the view here would be linked to the first endpoint, that first get endpoint. And so you'd be entering a actor ID here, a movie ID here, and clicking this get button that would cause your React app behind the scenes to essentially construct the the URL. By that I mean sort of construct this path here, and then just send a get request to your backend. Yeah. And the response that comes back from your backend, you can just put it in here in JSON form, right? Which would be the matching uh, the matching roles, I guess. Similarly, the second endpoint, it also had an actor ID, movie ID, and a language. Sorry, just going back to this one. Of course, if we leave out the movie ID and just we only have actor ID, then the get should return, what was it? It should return all, whatever the endpoint says, return all the matching entries with just that actor ID. Let me just check the endpoint again. I should know, but what does that endpoint do? Gets that movie/movie ID slash role. Oh, sorry. If you leave out the actor ID and you just have movie ID, then it should return all of the roles in that particular movie. So that would mean we would have a movie ID. We'd leave this blank, then click our get, and again, behind the scenes, your React app would the uh, construct the path and send the request back to your web API. And so the response should be a list of a JSON structure, which would really be an array of all of the roles. And you can just put or paste the JSON structure in here just to make sure you're getting the right response back. You don't have to sort of render the response in any kind of fancy way. This part of my UI would tackle the second endpoint, the second get endpoint. And again, the language may or may not be included, and one of these may not be included. And again, when we click the get button here, our React app will construct the correct path with the query string and it would send the request back to your backend, and the response that come back can be posted in here. And this part of my UI is dealing with the post endpoint. Okay, so you can do it that way, or if you want to, you could break these three up into three separate pages in your React app. I don't really mind how you design it, and it doesn't have to be, uh, you know, elegant in terms of CSS or any of that. Just something functional that works. So you need to put that together in order to uh, satisfy that part of the grading spectrum. Okay, if you want to hit this part of the grading spectrum, then you're going to have to just purchase a domain name. Again, as I said the last day, they're very cheap, so and make the necessary changes to the stack. The CDK project that I gave you there during the week, I gave you a link to the CDK project that uh, I was looking at in Tuesday's lecture. Yeah. Any questions about that, I wonder? No. Okay, let's move off into a different topic. So I want to start looking at the whole area of messaging, or alternatively, I could have titled this event-driven architectures. That their messaging is, admittedly, messaging is probably a slightly older term. Event driven is slightly newer, but they're completely interchangeable. So there's a lab. Now this lab is actually going to span out over a number of weeks, really, probably about 4 weeks, because the stuff that I need to cover is going to take me a number of lectures to get through. And you will be submitting this lab when you eventually get to complete it. So let's start digging into these slides. So we're looking at the title here is slightly different from the website, but they're all kind of there's a number of different terms that you could have used to kind of give a banner to all of this. So AWS integration and messaging services. Integration as in I guess integrating the logic parts, which in our case would be the lambdas. How we might get lambdas to communicate with one another. That's what we mean by integration here. And one way of doing that is using messaging services between the lambdas. Yeah. This is an image that we've seen before. I used this image in Rish when I was talking about serverless. Now, in a way, we haven't moved away from serverless. We're still uh, in that mode, if you like. But I'm extending it now to not just serverless, but message driven as well as being, it's kind of a second characteristic of the architectural style of backend that we're developing here. And as I said, message driven is also kind of referred to as event driven architectures. So serverless, comma message driven, a kind of a single title or label for it could be just event driven. And an event driven architecture or a serverless and message driven architecture, uh, it's broken up into a number of parts. There's the logic part, which in our case will be dominated by lambdas, but we could have used some other services. In particular, we could have used containerized based services. We've done a lot on containers in last semester. Containers are also supported on the AWS platform. They're slightly clumsy to use though, but they are definitely supported. And indeed, we could have implemented Kubernetes clusters on top of AWS. That is a very popular approach to use. It's a bit trickier though to do it. But as well as the logic part of an event-driven application, there needs to be some state management. We've looked at DynamoDB, or sorry, we looked at, yeah, DynamoDB, sorry, yeah. We've looked at, we haven't looked at any of the other ones. And we'll do a little bit on S3 in this part of it, but we won't cover it in any kind of great detail. And then there's the part of your application that deals with communication. Now, I could have put integration here as well. So that's the kind of link with the title in the first slide, communications and integration. And there are a number of services that fall into this category. We've already looked at API Gateway. In this section, we're going to look at two services, SQS and SNS. The other one we won't get to look at, Kinesis. So these two are going to dominate the best part of the remaining part of this module, in fact. Now, what I'm showing you here now doesn't involve using messaging at all. And in large serverless applications, you're going to have lots of lambdas, and maybe those lambdas need to communicate with one another. So, and that's what I'm trying to get across here. But the style of communication that we've got here between these lambdas would be classified as synchronous communication. What that means is, if you follow the flow and the numbering here, your client sends a request and triggers this lambda here. Now, we kind of know now there might be an API gateway here in between the client and the lambda. So that's kind of taken for granted. So it triggers this lambda, and this lambda, in order to complete whatever its purpose or its task is, it actually triggers another lambda to essentially, it kind of delegates to this lambda a certain responsibility. This lambda, in order to complete its task, it needs to communicate with this lambda. And eventually this lambda will complete whatever its function is. And any of these three might be talking to databases, they might be talking to other services. But when this one completes its task, then it responds back to this one. This one then maybe does some more number crunching, responds back eventually to this one. This one may need to do some more functionality, and eventually responds back to the client. Now, the problem with this, though, is that if there's certainly a certain spike in demand from clients, okay, there's just, for whatever reason, could be as online sales, and it's coming up to Christmas time or whatever, and there's certainly a high demand or a high volume of requests hitting this part of our application. And any one of these lambdas, their performance may degrade or reduce. The performance may reduce as a result of that, because of the nature of the processing that they're doing. But of course, and if we just say this lambda here doesn't do very well when it gets a high volume of requests, then its poor performance is effectively impacting on the performance of this entire suite of lambdas. And so the net effect then from the client's perspective is that you're going to experience latency. Yeah. So how do we overcome that problem? Also, if for whatever reason any one of these three lambdas is temporarily not available, then let's say this one is temporarily not available, maybe because it's busy, or the region it's located in is inaccessible from a networking perspective, then its unavailability is always going to impact on this overall piece of functionality. So spikes in demand, sudden spikes in traffic, and availability issues is going to have a negative effect on whatever processing is being done by this part of your application. Now, of course, you could argue, well, one way of getting rid of that is bring all of the functionality that we have scattered across these three lambdas and put it into one lambda. we no longer have availability related issues in that case. And the spike in demand really can deal with that as well to a degree, right? But the complexity now, we've gone from a nice modular approach to a more complex implementation. And we always prefer a more modular. So we'd like to hold on to this breakdown into multiple lambdas rather than having one large lambda, because we're back to kind of monolith approach in that case, in this case here. So all I'm documenting here now is kind of what I've been saying. So the problem with the first design, the tree lambda design, is that your lambdas are communicating synchronously, and synchronous communication is going to be impacted uh, if you have spikes in demand or unavailability of certain parts of your suite of lambdas at any particular point in time. So another way we could express it is to say that in our tree lambda approach, there's tight coupling between the lambdas, and tight coupling is always something we'd like to avoid. So I'm saying here, it's better to decouple your compute components. And the way we decouple them is by using some sort of messaging middleware or intermediaries between the individual lambdas. And in that case, what AWS provides is a number of services that we could use to satisfy that messaging aspect. The SQS service, which we'll look at first, SNS we'll look at then. Secondly, we'll have a quick look at data streams as well at the very end. And the use cases for these will depend on the nature of the application itself, right? So there are cases when SQS is the right choice. There are cases when SNS is the right choice. And, so maybe if I go on to the next slide, in very simple terms, this is kind of what we're doing now. We're introducing this messaging infrastructure into our architecture. And so now the flow is client triggers this lambda. This lambda now no longer communicates directly with this one, but it is communicating kind of indirectly in the sense that previously it would have sent some sort of payload to this lambda, but now it puts the payload into or gives it to some sort of messaging infrastructure. And this lambda here then kind of periodically checks, are there any messages in here for me? And if the messaging infrastructure says, yeah, there are, here are a batch of messages. So there could be more than one because, in the case of the high volume, there may be a number of requests that are kind of batched inside in this structure here. And so this lambda then grabs a batch and does its processing. And in a similar way, it uses messaging infrastructure to communicate indirectly with this lambda. But in terms of the client, the client will get its response back once this lambda has completed its processing. And by that I mean it has done whatever processing it needs to do. It has placed a message into this kind of queue or data structure here. It's a queue really, I guess, yeah. And once the queue, whatever's managing the queue, once that responds to say, I've received your message, then this Lambda can complete its execution and it can respond back. Now, of course, this only works, right, if the nature of the processing that's being done by these two Lambdas is such that your client doesn't need to wait for this processing to complete. Okay, maybe the client needs to be informed at a later stage that the processing done here has been completed, but it doesn't need to know it immediately, right? So this will only work if that is the case. If that isn't the case, then we're back to, you know, requiring synchronous communication between them. But in many cases, we don't need that synchronous communication. So what we're really kind of interested in is how do we set this up from an infrastructure point of view? And if I go back now to the previous screen, so the benefit of introducing this messaging kind of intermediaries between your lambdas is you get reduced latency. Okay, your client is now only waiting for the first lambda to complete its functionality. You get increased availability. By that I mean, if for whatever reason, let's say this lambda is temporarily unavailable, then the messages that are here, which it needs to process, they will remain there. They will persist. They will persist there until the lambda is back up and available again. Okay, so there are no real issues with the temporary unavailability of these two lambdas. Obviously, if this lambda is unavailable temporarily, then that does impact on your client, but not for the other two. Other advantages, availability, reduced complexity. Well, the reduced complexity is because we've broken up the overall functionality up into three lambdas rather than having one large lambda. Yeah, and also there's reduced complexity because there's no longer tight coupling now between. I jump again. In a way, there isn't tight coupling between these lambdas anymore. Yeah. So that's kind of the big picture. And the first messaging service that we're going to look at is called SQS, or Simple Queue Service. Now, the thing that is that this SQS service was the very first service that AWS provided, even before EC2, certainly before Lambda. It was the very first one. And the use case for SQS back in 2006 was to satisfy a need where customers had applications running perhaps on their own servers, or they could have been running on cloud service. They wouldn't even have, EC2 didn't exist. So more than likely, we had applications running on in-house servers. But those applications, and these could be both owned by the same organization, or these could be different organizations. And there was a need to have these, or to enable these applications to communicate with one another. And that's where SQS, the need for SQS came from. So now this application would, send a message to the SQS service, which was being managed by AWS. And this application on the right would periodically check to see if there were any messages for it in this queue here. Yeah. Now later on, where SQS was being used was when we had our applications running on EC2 instances. But now, where we're interested in using SQS is where we've got just lambdas actually talking to each other. And the lambdas again could be part of the same application, or they could be lambdas that are parts of separate applications. So this is where we're kind of interested in down here. So we now have client sends request to API gateway. API gateway triggers talks to the Lambda service, or to a Lambda, let's say. Lambda puts a message into a queue, and this Lambda over here then periodically grabs the messages from that queue and does its thing. And as well, we would classify SQS now as serverless, but certainly back in 2006, the term serverless didn't exist. But in order to use the SQS service, in a sense, we we as developers, we didn't have to set up SQS servers. The AWS kind of platform took care of that for us. So in that sense, it was serverless before the term even existed. So what is SQS? It's fully managed. We know that that's a byword for serverless today. It's fully managed. It's distributed. I'll explain the distributed nature of it a little bit later on. So we'll kind of skip over that as to what I mean by that. And it's used to decouple, that's fine, decouple applications, as in this case here, or decouple components, as in lambdas. We can refer to our lambdas as components within a larger application or components which are part of separate applications. You compute components, well, okay, in terms of the two main kind of actors in this, we have producers and consumers. That's what we refer to them as. So a producer is an application or a component that writes messages to your queue. So if I go back to the previous slide, we would say this is a producer component, whereas this one here is a consumer, and it's also a producer, as it turns out. This component here is just a consumer. Okay, so that's just the terminology. It's pretty simple. High level characteristics of this SQS service. It's highly scalable. There is essentially no limit to how many messages you can pump into an SQS queue. Even if the consumers are not processing them quickly enough, you're never going to get to a stage where your SQS queue is full and it can't receive any more or can't accept any more kind of write operations on it. So it's highly scalable. It's also scalable on the consuming side, and I'll explain that later on as to what I mean by that. So there's unlimited throughput, unlimited number of messages. That's fine in a queue. There's a certain amount of persistence. By default, an SQS queue will hold on to a message for 4 days is the default, but you can actually configure that. The maximum is 14 days. So you don't get long-term persistence of your messages. If you want that, then you're probably using some sort of database. But there is kind of short to medium term persistence. And that's because, your consumers may be busy or they may be temporarily unavailable. So that's why there's a certain level of persistence or retention, as they're calling it here. Low latency, there are certain guarantees from AWS's perspective. There are guarantees on the producer side and on the consumer side. On the producer side, in the sense that if a producer wants to write a message to a queue, then AWS will guarantee that the SQS service will accept them and place them in the queue within a certain minimum time period. Okay, so you don't get any kind of delay. And similarly, on the consumer side, if the consumer asks SQS, have you got any messages for us? Then there are guarantees as to how quickly SQS will actually respond back with either a yay or nay. You can write messages in batches, but there's an upper limit. So you can't write more than 10, you can't have more than 10 messages in a batch. Don't know why they set that limit, but it is a limit anyway. And I guess probably the reason they set that limit is to ensure that the guarantees that AWS states that in terms of latency, the response time guarantees that they quote in their documentation can be met. There is a limit on the size of a message, or 250 kilobytes. There's ways of overcoming that limit if your messages are larger than that. essentially the way it works, if your messages are larger than that, is you put the bulk of the message into, let's say, an S3 bucket, and the actual message that you write to your SQS will contain a reference to the bucket object that contains the body of the message. Okay, that's just the way you overcome it. And again, I would say that this upper limit on the message size, again, is to ensure that whatever latency guarantees that AWS states that the SQS service will not exceed is uh, that's why the limit is stated, I'd imagine. Caveats. Oh yeah. Um, Again, this kind of comes from obviously from testing that they've done on the SQS service in the early days. Uh, Again, the documentation says that there may be duplicates of a message. So a consumer may actually receive more than one copy of a message. It's very rare, but it can happen. And so AWS has to state that, I guess, in its documentation. So duplicate messages may occur. Uh, and so if that's the case, then your consumer, the way you implement your consumer, it has to be implemented in an idempotent manner. We won't go into how you satisfy this idempotency requirement, but it's something that you have to build into your implementation of your consumers. The second caveat is there is no AWS will not guarantee that the messages received by the consumer will be in a particular order. They certainly won't be in the order that the messages were written to the queue. And we will see evidence of that. Even in very simple cases, you can see that occurring. Where we will put the messages in one order, but the consumer receives them in a different order. If order is very important to you, you can configure a queue to ensure that a consumer gets the items in the correct order, but the documentation states that that is going to impact on the performance of SQS. So you're going to get greater latency in your responses from SQS if you have a need for ensuring that your messages are consumed in the same order in which they were written to the queue, which is not usually the case, but it can be. Okay, so from your two actors, as I call them, your producers and your consumer, a producer is obviously just going to be publishing or writing messages to a queue. And SQS, sorry, where am I? There. SQS, like every other service, it has an SDK. So we will be using the SDK to communicate with SQS. We don't have to kind of write raw HTTP type uh, requests to it. Like SQS has an API, web API interface, but we won't be interacting with the web API interface directly. We will be using the SDK to do that for us. So that's fine. SQS then, when a producer publishes or writes a message to a queue, SQS will persist it, the message. It will persist it either A, until a consumer actually reads it, or if the TTL, the time to live for the message, expires. So TTL is an attribute that you can set for a message that the publisher would set for a message when he writes it to the queue. So if in either of these cases, the message will eventually be removed from the queue. The consumer either consumes it or its TTL would expire before a consumer reads the message. That's okay. From the consumer's point of view, now the consumer polls the SQS service periodically. Now, the consequence of that is when a producer writes a message to a queue, the consumer isn't informed about this straight away, right? If that was the case, then we're essentially back to synchronous communication. So the consumer periodically, and you can control the frequency of the polling, but the consumer polls SQS, essentially kind of asking it, do you have any messages in QA for me? SQS will return, and it always returns a batch of messages. Or put another way, the consumer has to assume that what it receives in the response it receives from SQS will be a batch of messages. Even if there's only one message, then it has to treat it as essentially an array. Um, so it receives a batch of messages, and the batch is always going to be less than 10. That's that 10 kind of limit was mentioned in an earlier slide. Uh, so even if there are more than 10 messages available, then SQS will only return the first, or it will return 10 of them. And that means the consumer has to poll a second time before it gets the rest of the messages. It'll never get more than 10 in a response back from SQS. So the consumer receives a batch of messages, it processes that batch, and importantly, uh, the consumer, it must tell SQS to delete the messages that it has processed. So it's the responsibility of the consumer to tell SQS to delete messages once it has received them and processed them. Just because the consumer receives a batch of messages from SQS, SQS will not delete them straight away, because it's possible that during the processing of the batch of messages, maybe the consumer throws an exception, right? In other words, it hasn't completed processing the batch. And if that arises, then it makes sense that the messages should be left in the queue and maybe given back to the consumer the next time it does a poll. So the consumer always has to explicitly tell SQS to delete all of the messages that it gave it in the most recent batch. And SQS will know which messages were in the batch that it gave to the consumer. And we'll see in a second, later on how it knows that. Kind of visual representation now of what we've been saying so far. So you've got this producer. It's communicating synchronously with SQS. So it does wait until SQS acknowledges the receipt of the message or batch of messages that the producer wants to write to the queue. On the consumer side, it's polling the SQS service, asking it for a batch of relevant messages. And, to complete the kind of picture, there is kind of asynchronous. We could regard the communication between these two lambdas because they are linked, obviously, in a certain way, but the communication or integration is asynchronous in that this lambda is not waiting for this lambda to complete its processing of messages. How are we on time? Okay. A little bit more on the generalities of SQS. Uh, Encryption is kind of built into it. So if I go back to here, the communication between our producer and our SQS, the actual messages themselves are encrypted in transit, as we say. The messages are also encrypted when they're persisted in the queue, and there's encryption between the consumer and SQS as well. So that's just kind of for free. Yeah. So there's both at rest and in transit encryption, as we term it. Security is obviously an issue. There's IAM will play a role. So the producer needs to have the necessary IAM policies to allow it to write to the queue, and the consumer has to have the necessary IAM permissions to read from the queue. You also have what are called SQS access policies, where these are concerned with is if you want to make an SQS queue available to Lambdas that are running in a different AWS account from your own account, you essentially need to give the other account the necessary permissions to use your queue. Yeah. And also where these access policies, as they're termed, SQS access policies, where these are important is like up to now, I've been giving the impression that it's only Lambdas that might be producers or consumers, but that's not the case. Other services could also be both producers and consumers of an SQS queue, and we will see instances of that later on. But if you have some other service that could either be a producer or a consumer, that other service component needs to have the necessary permissions to play the role of a producer or consumer. Demo time. This is as simple as I could make the demo now. So I have a Lambda function that I want to be a consumer. And I'm going to have an SQS queue. The SQS queue is managed by the SQS service. And my producer, in my case, will just be the AWS CLI. Okay, so it's going to be writing messages to an SQS queue, and my Lambda over here is going to be consuming those messages. Now, when a Lambda is a consumer, it's actually the Lambda service that does a lot of the work for you. It's the Lambda service that is actually the consumer, not the Lambda function itself. So when we look at the code for this Lambda, it won't be interacting with the SQS service directly at all. Right? And that is because the way it actually works with Lambda is the Lambda service, it's going to be responsible for polling the SQS service, asking it for if there are any messages in the queue. SQS, let's say it responds with a batch of messages. What the Lambda service does then is it puts those messages into a local kind of temporary data structure. It's kind of a queue as well, but it's not an SQS queue. It's a local queue structure. And the Lambda service invokes the Lambda function. And in the event object parameter of the Lambda function, that's where it will put the batch of messages that it received from SQS. So that's how it actually works underneath the hood when a Lambda is a consumer. And that's what I'm alluding to down here. Remember we said the consumer is responsible for telling SQS to delete the batch of messages that it received from it once the consumer has processed the batch. Well, that in this case, the Lambda service, because that is our actual consumer, it's not really the Lambda function. The Lambda service will take care of communicating to SQS that the batch of messages that it received should now be deleted. Now, it will only do that if the actual Lambda function exits successfully, as long as it doesn't throw an exception or perhaps return a throttling response. So as long as everything goes smoothly in the execution of your Lambda function, then if everything does go smoothly, that will allow the Lambda service to request SQS to delete the batch of messages. That doesn't arise, let's say it does throw an exception. In that case, uh, the Lambda service will not tell it to delete it. And automatically then, because SQS never receives the delete uh, instruction, then it will leave the batch of messages in the queue. So the next time the Lambda service polls it, it potentially will receive the same batch of messages. And that makes sense because my Lambda never completed the processing of that entire batch. And that's why the Lambda implementation, the Lambda function implementation needs to be idempotent because it could potentially receive the same batch of messages more than once. Okay, so uh, let's do it from here actually. So from a CDK point of view, how do I set up all of this infrastructure? Well, it's pretty straightforward, really. This is how we create a queue. Again, this is another L2 construct. So there's a nice convenient L2 construct available to us. So this is creating the queue. Uh, and, like every L2 construct has three parameters: the scope, some sort of a unique identifier for this L2 construct. Now, in this particular case, I'm not doing any extra configuration of the queue, but there are certainly a number of configuration uh, options available to you. We'll see some of them later on, but in this case, I'm accepting all of the default configuration settings. Here's my Lambda function. This is my Lambda consumer, and there's nothing exceptional here. Note, I'm not passing in as an environment variable a reference to the queue. And that kind of reinforces the point that I've been making up to now, that your Lambda function, it doesn't talk directly to the SQS service at all. The Lambda service does it on its behalf. So that's fine. This here then is how we essentially, um, how we tell the Lambda service, I suppose, that this Lambda function needs to be a consumer for my queue. Okay. So it's kind of a two-step process. You first of all create an event source. So there's this, this is another L2 construct. So there's this SQS event source, and we're kind of connecting this event source to our queue. And then we're making the event here, we're making the event source a trigger for our Lambda. So as I say, it's kind of a two-step process. Create your event source object first, and then link that event source as a trigger for your Lambda. So that's it really, yeah. The only thing all I'm doing here then is I'm outputting the queues. Like a queue will have a URL. That's how we communicate with it. And I'm just outputting the queues URL here from the stack because I'm going to be using that URL in my AWS CLI invocation because I'm using the AWS CLI as my producer. So we're saying lambdas require triggers. That's okay. Here the events. Well, that's okay. I've kind of explained that. So it's as simple as that, really. That's how we ensure that this Lambda is going to receive messages from our queue, even though it's the Lambda service. We'll do the polling and all of the kind of messy stuff behind the scenes. Producer and consumer. Oh yeah. This is an excerpt from my consumer Lambda, and the messages themselves will be buried inside in the event object that it receives. And in particular, you've got to access a property called records in your event object. And the records property will be an array, its value will be an array, and the array is going to be the batch of messages that were received from the queue. Yeah. It's always going to be a batch, I said, even though there may be only one message in the batch, it's always going to be a batch. So that's why we're iterating over the batch of messages. And I'm just console logging the actual message itself within a particular element in my array. Yeah. So it's as simple as that. Uh, okay, because my producer is the going to be the AWS CLI. This is how we send messages to a queue from the command line, if you like. Now I've already deployed. Will I look at the code? No, I won't yet. What I'm showing you here is a screenshot of. Sorry if I go back. See here where I've got a console log at the beginning of my Lambda. We always do this because we're always interested in, certainly as learners anyway, we're interested in what is the structure of the event object, okay? And we've done that when, we were using API Gateway, and API Gateway was the event source for our Lambda. Um, Here, the event source is uh, SQS, kind of, yeah. But when I console log the event object, in this case, this is what it's going to look like. And you see here, I'm pointing you to, there's a property within the event object called the records property. And that's an array. And from this screenshot anyway, there looks like there's only one entry in this array because it's an object that begins here. And where does it end? It ends down here. Okay, and that's the end of the array here. So there's only one message in the batch. So this is one message. And the message has a number of, it's an object, right? It has a number of properties. The body property, that's where we will find the actual message payload, if you like. Yeah, the other things are kind of attributes that are added on by the SQS service itself, like a message ID and other stuff. Yeah. So it's this body property. That's where you'll find the actual payload of the message that was written by the producer. Now, if I go back to the previous slide, because I was using the CLI, then my message was the message body here was just a string, hello world. Usually, though, it's going to be a JSON structure, but it's just a string. And so if we look at the body property here, here's our string. Yeah. Um, that's okay, I think. Let me just do a quick demo of it, I suppose. So I have deployed it already. It's not that one. I can close that off. Nearly running out of time, but I'm just going to quickly do this demo and then I'll stop the lecture. Oh yeah, here we go. So here's my CDK project. Here's my CDK stack file, which I've talked to you about. I've shown you that. Here's my Lambda, my consumer, which we've looked at. And so I've deployed it already, as I said. So I can now go, I do a clear, and I ran it earlier on. So if I just bring it back up. So there you go, SQS, AWS, SQS, send message and all the rest. This is the message So this is the queue URL, which was outputted to the command line when I deployed it. And, or is that the right one? Oh yeah, here's my message body. So let's send something different actually this time. So let's say hello world from lecture. Send that. Q to quit out of that. So I've sent a message to the SQS service. The SQS service has placed the message into the queue using the URL of the queue that I gave it. On the other side, the Lambda service uh, periodically polls that queue, and I didn't set the polling rate, but I think I'm not sure what the default is. Is it every 5 seconds maybe, or perhaps 10 seconds? It polls it, and it would have polled it by now. It would have received the message batch, which only consisted of one message, and it would have triggered my Lambda. And so if I go to Cloud, because my Lambda has console logs, I can go to CloudWatch logs for the Lambda. So let's just go into the watch, CloudWatch. Down to my log management. Here's the log group for the consumer. We can see here, like, well, okay, I can tell you that this is the log group for the consumer Lambda. Go into the log stream. And if we look at the console log of the event itself, this is what I showed you. And here's the body here. Hello world from lecture. So that all looks good. My Lambda was triggered and it received a batch of one, if you like. Here's the records property and all the rest. Yeah, so that all seemed to work fine. Now, in terms of the lab, in the lab we do something slightly more advanced, where we're actually using an S3 bucket. And so the user is uploading images, I think in this case, to an S3 bucket. And the S3 bucket is the producer. And that writes messages to our SQS queue. And there's a Lambda being triggered at the other end. Now, okay, I think, you can, because of the nature of these labs, they're very prescriptive and all of that, you can actually certainly do section one of this lab. I wouldn't go into this one here, SNS, because that's another messaging service, which we will look at probably in 2 lectures' time. But you can certainly work your way through the first part of this lab immediately. Okay, that's it. As usual, I'll allow any questions in case there's anybody still listening and has any questions for me about this or maybe the assignment before I wrap up. No? Okay, that's fine. I'll turn up for the lab tomorrow as usual. So I'll either talk to you then or I'll talk to you next week. Thanks. Bye-bye.